Black holes, the mass of a mountain, squeezed into a volume smaller than a proton, could be drifting through our solar system right now, and we would almost certainly have no idea they were there. When most people hear black hole, they picture the corpse of a massive star, collapsed under its own gravity. That's the textbook version. A star at least about 20 times the mass of the Sun burns through its nuclear fuel, can no longer support its own weight, and its core implodes. If the collapsing core is heavy enough, roughly 3 solar masses or more, it forms a stellar mass black hole. These are the ones we see in X-ray binaries, or merging in LIGO's gravitational wave detections. But there's a problem. Some black holes we infer in the universe are too light, too old, or too strangely distributed to be easily explained by dying stars alone. That's where a much weirder idea enters: primordial black holes. Primordial here means from the very beginning. Instead of forming billions of years after the Big Bang from stars, primordial black holes would have formed minutes, hours, or even fractions of a second after the Big Bang itself. To see how, we need to rewind the universe to when it was smaller than an atom, hotter than the core of any star, and filled not with galaxies, but with a nearly uniform soup of energy and elementary particles. In this early plasma, gravity was already at work, tugging on tiny variations in density, regions that were slightly more crowded than their surroundings. Normally, these overdense regions just grow slowly, eventually becoming galaxies. But under the right conditions, if a region was dense enough and compact enough, gravity could crush it past the point of no return and make a black hole directly from the primordial fireball. Think of the early universe like a pot of violently boiling water. Most bubbles are small ripples, but occasionally, a big bubble forms and collapses. In cosmology, those big bubbles are unusually large density fluctuations. If a fluctuation on some scale was strong enough, its own gravity would overwhelm the pressure of the hot plasma trying to push it apart. Once that happened, there was no stable configuration. The region would collapse inside its own Schwarzschild radius, the critical radius where escape velocity exceeds the speed of light, and a black hole would form. Crucially, the mass of that black hole would be tied to the mass contained in the horizon of the universe at that time, which depends on how old the universe is. Earlier times mean smaller horizons, and therefore smaller primordial black holes. Later times mean larger ones. This timing gives primordial black holes an enormous possible mass range. If one formed about 10 degrees seconds after the Big Bang, it might weigh as little as 1 trillion kilograms, roughly the mass of a large mountain, yet be smaller than a proton. If it formed about 1 second after the Big Bang, it could be as massive as our Sun. Forming even later could, in principle, produce black holes with millions of solar masses, similar to the supermassive black holes we see in galactic centers. That's a key difference from stellar black holes, which are constrained by how massive stars can get and how they die. Primordial black holes are limited instead by the physics of the early universe, the expansion rate, the temperature, and the spectrum of density fluctuations seeded by inflation. So how are primordial black holes different from the black holes made by dying stars? In one sense, they're not different at all. General relativity tells us that once a black hole settles down, it's fully described by just a few parameters: mass, spin, and electric charge. There's no tag that says, "I was born from a star," or "I came from the Big Bang." This is sometimes summarized as black holes have no hair. A 10 solar mass primordial black hole and a 10 solar mass stellar black hole, isolated in space, would curve space-time in exactly the same way, but statistically they should live in different environments. Stellar black holes tend to live where stars are or were, in galaxies, in star-forming regions, in binaries. Primordial black holes could be scattered more diffusely, even wandering the outskirts of galaxies or the vast dark spaces between them. Their mass distribution might also be very different. Stellar evolution gives you a certain range of black hole masses, mostly from a few to maybe tens of solar masses, with some outliers. Primordial black holes could cluster around very specific masses, depending on the details of the early universe. For example, a brief phase transition, when the universe changed state, like water freezing into ice, could temporarily enhance density fluctuations at one particular scale, producing a spike of black holes all around, say, asteroid mass or lunar mass. Observationally, if we saw an unexpected population of black holes with masses that don't match what we expect from stars, especially in places where stars never lived, that would be a strong hint that some of them are primordial. There's another twist. The smallest primordial black holes might not exist anymore. According to Stephen Hawking's theory of black hole evaporation, black holes aren't perfectly black. Quantum effects near the event horizon allow them to emit radiation, very slowly losing mass over time. The smaller the black hole, the faster it evaporates. A black hole with a mass of about 10.28 kilograms would evaporate in roughly the current age of the universe, about 13.8 billion years. That means any primordial black holes lighter than that would have completely disappeared by now in a final burst of high-energy gamma rays. Heavier ones would still be around, quietly drifting through space, essentially invisible unless they interact with matter or bend light from background objects through gravitational lensing. Why do cosmologists care so much about these hypothetical relics? Because if primordial black holes exist in the right numbers and masses, they could solve several puzzles at once. One big puzzle is dark matter, the invisible mass that makes up about 85% of the matter in the universe, inferred from galaxy rotation curves, gravitational lensing, and the cosmic microwave background. For decades, people have asked, could dark matter simply be made of lots of tiny black holes? Observations have ruled out primordial black holes as the dominant form of dark matter over many mass ranges, especially around the mass of the Moon and above, but there are still windows where they could contribute a fraction, or in some scenarios, even most, of the dark matter. Another puzzle is how supermassive black holes grew so quickly in the early universe. Primordial black holes could have acted as seeds that jump-started that growth.